Okay, welcome in. This video, we're going to talk about functions, very important sort of object, I guess is the word for it in R. Essentially, what a function does is it takes a bunch of code, a piece of code, a bunch of lines of code, and it packages it together into one specific tool that you can then use over and over and over. There are a ton of functions that we use all the time in R. For example, the sum function, if we want to sum the numbers from 1 to 10, remember this colon just means we're getting the integers 1 to 10, which I've printed out here. If I want to sum the numbers 1 to 10, I just use the sum function and apply that, and I get the sum of the numbers from 1 to 10 is 55. If I want the mean of the numbers 1 to 10, I just use mean. And these are both functions, sum and mean. You can tell they're functions because there's a word and then there's parentheses, which indicate the function is taking something in as its input. If I just typed in sum here, R would tell me that yes, sum is a function, and this kind of mumbo jumbo here is something beyond what we're going to talk about today. Today, we're going to be defining our own function and kind of seeing how that works. So we have this nice function for sum, mean. I don't know of a function in R that takes exponents. So for example, if you want to do 4 to the power of 9, you kind of have to type it out or something like that. And that's okay. That's not like that much work, but we're going to build a function for it just so we can kind of get the sense of how that works. So the first thing to do is define the name for our function. And I think naming conventions are very important in any type of programming. In R especially, you want to remember what's a function, what's not. So I always start my name of a function with capital FUN, underscore, and then the name of the function. This way, when you come back to it, if you just name it like square or something, you're like, what is square? Is it a constant? Is it a variable? So what, I just like to name it. And then we assign it as a function. And you can see as soon as I type function, it turns orange. This is a special word in R. And what's going to happen is you see I put these parentheses here and these curly braces here. These parentheses are going to tell us where we put our arguments for the function, which I'm going to explain in a second. And these curly braces are actually where the actual code goes. So the arguments of the function are the inputs of the function. If, for example, for sum in the sum function and this mean function, the inputs, the arguments were these numbers 1 to 10. It was a vector of 1 to 10. In this case, for fun square, we are going to have two arguments. We're going to have the argument x, which is going to be the number that we want to actually take the power to, and we'll say p is the power that we want to take x to. In fact, let's just start really simply. Let's just start with x. So you're going to say it's a function of x, where x is the argument we pass in, and then within our actual code, we are going to say x to the power of 2, and this is what within our code. And notice that nowhere on this page is x defined. X is not in my environment. If I ran this code by itself, I would get an error. But because x is defined as an argument, the function knows that we're going to be passing in the value of x when we actually run it. So the last part, the last part of the function is I just have to return. And notice when I type return, it turns orange. It's an important word. Return just means this is going to be the output of x, the output of the function. And there can be functions where you don't return anything, which is a little bit like more subtle, but in this case, we want to return something. So returning x squared, and we just define our function. And now you can see the code ran. Nothing really happened, but the code did run in our environment. We now have this function. It's been saved. Yeah. That to go away. And now if I call the function, first of all, I load the function up and I had the parentheses. If I hit the tab button, it's going to prompt me really nice and say, what do you want x to equal? I'm going to say, I'm going to make x equal 7. If I hit enter, what am I going to get? Get 49, because x is equal to 7. 7 gets passed here. 7 squared is 49, and 49 gets returned. And if we want to make this more advanced, we want to make some multi-argument function. We can also pass y as our argument of this function, and then or let's make it p. That's easier to remember. We're going to pass p, and then p is going to be the function that we raise it to the power of. So maybe in this case, instead of fun square, it's going to be fun power. We're taking the power of something. So fun power, and then let's say we want to take 2 to the power of 10. And we're going to get 1024 because we're saying x equals 2, that goes here. p equals 10, that goes here. We return to the power 10. One cool thing is we don't need this return if you kind of want to be more minimalist, and the last like item that you kind of print to the console within your function will get returned. So if I redefine this, it will still return x to the p. I like to do return just so I can visually see when the function is done, but that's up to you. And there are other cool things we can add, like other standard kind of programming techniques. For example, if I tried to run this, so I said hi, which is a character, as my x value, and then 10, which is p, as my p value, not p value, but as my value of p in that's a statistics joke. In this function, I'm going to get an error because I'm trying to take, essentially what I'm doing is I'm saying x is high, that pi goes here, I have a 10 here. So essentially what I'm doing is in the function is high to the power of 10. That doesn't work for the exact reason that it's a non-numeric argument, high to a binary operator. Okay, so it's not going to work. So if you want, you could add some error checking yourself. And one thing that we can do is we can say, for example, the class of 10 in R, the class of the number 10 is numeric, but the class of character of pi is a character. So one thing you can do from the start is check if, remember our if statements, class of x does not equal to numeric. So if x is not a numeric, right, we can return, please enter numbers. And this is telling us like, this is if it's true that x is not a numeric, we're just going to return right away, and return, we're not going to go to anything below the code here, and we're going to tell the user to enter numbers. So let's see if that works. Fun power I 10, boom, please enter numbers. So it's nicer, it's not an error. Like from R, it's a little bit more clear. You have to enter numbers instead of a character. And you can do this for P as well instead of X if you want to. I'm just going to show the X version here. And remember, like once we hit return, once something is returned, nothing else is returned. So that's kind of important to remember as well. Okay, so let's do a little bit of slightly more advanced functions. A function, I'm going to do a simulation function. I'm going to call it fun_sim, where sim is simulation. And I'm going to define it in the usual way. So I have a function with, I have my arguments in here and then my code in here. We're going to define x as our starting point for the simulation. And we're going to define n sims. The n is the number of sims. And here we're going to say equals 1,000. And this is interesting because in the previous case, I just had x and p. I didn't define what x and p were right off the bat. This, I forget what the specific word for it is, evading me at the moment, but I think it's like an optional argument, but we're going to see why we did this in a minute. So just hang tight with that. And within the code, I'm going to have, within the function, I'm going to have a little bit more complicated code. So here in the previous function, I just like had one-liners. In this case, I'm going to write a for loop, which we've talked about in a previous video. We're going to go from 1 to n sims. And each time we go through the loop, we're going to tack on a new value of x, which we draw just a random number, which we do from our norm, which we're going to, our norm 1, which we're going to talk about in a different video, but this is saying random normal draw and just draw one value. So random number, random number, random number. So we're going to tack on the C is concatenate. It means bind things together. So we bind X. And we're going to just add on a random normal. So for example, if I start with X equals 0, and then I concatenate X, R norm 1, that's 0, add on a random number. And if I do that again, I'm just going to get a different random number because I'm concatenating 0 with a random number, and you sort of get the point. So a cool little just kind of tacking on random numbers to the end of X each time. And then my last but not least, I'm going to return X. So I can define this function and then I can run it. And here is what's cool. So what's nice is that I can define my start where I want to start as X. Because I defined the argument n sims as 1,000 when I define the function, I don't actually have to explicitly, I think it's an implicit argument. I think that's the official name. I don't have to explicitly define n sims when I call fun sim. I can ignore it. In my previous function, if I did fun power x equals 2 and I didn't define p, it's going to say argument p is missing with no default. There's no default value that like fun power knows to go to because I didn't define it here. But in FunSim, there is a default value of NSIMS. I set it as 1,000 here, so it's an optional argument. So this will run A-OK. And you can see it's a little bit ugly. Let's just look at the head. But you can see it is indeed a random kind of walk of X. It's not even a random walk. It's just a 0 plus a random number. If I wanted to make it a random walk, I would have to, sorry. I realized in the setup. So we want to take the last value of X, which is tail X1, and add on a random number so that we're actually like kind of moving through time and adding on to X. So in this case, let's just like save some data as I'm doing the same thing. I'm just saving data. I'm saving the value of the output as data. I'll do it in here so it's easier to see. And again, X equals 0. I don't have to specify NSIMS because there's a default. I have data, and then it's saved, and within data, I have all these numbers, and we can plot data nice and easy with the plot function. I got figure margins too large, which means my plot window is not big enough, and there is my data, and it's a little bit squished, but you can see it's just kind of this random walk around and the index goes from 0 to, it's going to be 1,001 because we started out with X equals 0 and we added 1,000 more values, but you can't tell that it's 1,001 here. And again, just to reiterate, the only reason the thing I changed here was that instead of just adding on a random number to the end of X, we add the last value of X plus a random number. So you kind of get this like moving around sense. If I didn't have if I wasn't adding on to the tail of X and I simulated this and then I just plotted the data, it's just going to look very random, just random numbers throughout time. So that's why I did the tail of X thing. But anyways, hopefully that helps with functions. Again, if you're finding yourself running the same code over and over, as you can see, it's much simpler just to define it as a function and then call the function, because the function will just run the code over and over for you. And these are relatively simple versions of functions, but you can see them getting very complicated. And it's nice to define them in a package and then just call that package whenever you need to. And a function can do all kinds of things for all kinds of data. So hopefully this has helped convince you of that. We'll see you next time.